Okay, I'm going to go ahead and get started. If you did that little take-home problem, I will collect that now. So if you have it. Are you a new student?
I am. It's funny.
Wow, what a change. Like, really? Wow, it's drastic, man. Why'd you do it? Just to do it, or?
No, I went to like trim it up.
Messed up?
Completely messed up.
Oh, that's funny. Do you have something you want to name? Yeah. Something, right? Thank you. Okay, let's get going here. All right, so this is the last section of chapter 7, and there's several different topics within this section. What they're doing in this section is trying to just draw the whole chapter to a close by showing you some of the things you can do in respects to physics and engineering. And the main three things in this section that they cover is the idea of work. They talk a little bit about hydrostatic pressure. And they talk about, last thing, the center of mass. And another word for that is the centroid. So as an instructor, I really don't have time to go through all three of these. So I just kind of pick one. And normally, if you go back and look at any of my other lectures from my YouTube channel, I normally cover center of mass. And it's just a formula, and then we find centers of mass, and it's real fun. But this time, I think I'm going to do work. And we're only going to do one example. That's it. And the idea is that you get to a physics class or an engineering class, how do we implement the integral to help us solve problems? All right? And there's no like cookie cutter way that we do it. Every problem is unique. So I'm going to start with the problem here. We're going to think about it, and then we're going to use the integration to get to a solution. All right? So we need to get some preliminary stuff out of the way first. Do you even know what work is? Okay, in terms of a physics term. Not like, hey, I work for a living, huh? Okay, so in physics, work is defined to be force times distance. And now that can get even more complicated. The distance can actually be a displacement vector and everything. Here we're looking at straight line motion. So if you're going to move an object from one point to another through a straight line. If that's the case, then if you take the force and multiply it times the distance, compute that value, that will give you work. Okay? So if I have my little tissue because I'm not feeling well today. If I take my tissue box and I put it here and I want to slide it across, then I have to apply a force to it, and then I've moved it from there to there. I have done work. Okay, the force I applied times the distance equals the work I did. All right? So we need that. Now, what is force? Well, force comes from one of Newton's laws of motion, is mass times acceleration. So if you have an object, it has mass. And acceleration is, well, it's the second derivative of position, isn't it? If you look at a position function, first derivative is velocity, second derivative is acceleration. So if you somehow know how the mass is accelerating, then the mass times that acceleration will give you your force. So that means that we have a way of actually computing what force is. Now, typically when we do mass, we like to measure mass in kilograms. And when it comes to acceleration, we like to measure that in like meters per second squared. So those are the units that we like to use for those. Those aren't the only units, but those are the ones that are most commonly used. Now, if we are talking about an object on Earth where you're just going to be moving the object, like let's say I take my little spray bottle here, and let's say I just want to lift it up, right? And I want to move it from here straight up to there, then I have a displacement, right? A distance that I traveled, and the force that I actually applied was just to counteract the force of gravity. Gravity is the only force acting on that bottle right now. So I have to overcome that to move it. So we replaced the A with gravity, okay? So if A, the acceleration is gravity, then A becomes, we use G instead for gravity. A becomes G, and that on Earth is 9.8 meters per second squared. Now, a lot of you that take physics classes will say, hey, well, why isn't that negative, right? Because downward force. I agree, it is, but when it comes to forces, it's always relative. It's kind of like, if I'm walking towards Muhammad, am I moving in a positive direction or a negative? Well, to me it might be positive, but to him it might be negative. So everything is relative, okay, to your position. So if I put 9.8, we could use negative 9.8, but I'm going to use positive, all right? That look familiar? You seen that before? Okay. What else? What else do we need? I'm just getting us set up for this problem, all right? The other thing I want to mention is this thing called density. Okay? Density is what? You know the definition of density? Like if I say how dense something is, isn't that how much stuff is like packed into it? Like if you take a cotton ball, it's not very dense, right? You take a baseball, that is very dense. Agreed? But what is its mathematical equation? Density is equal to, I heard someone say it, mass over volume, m over v, okay? Mass over volume. And we can use m and v. Now this mass is the same mass that's here, okay? That means that if I ever wanted to, I have this equation that relates mass, density, and volume together. I could solve this for mass, couldn't I? If I solved this for mass, I would get mass is density times volume. Right? Okay, one other thing we need before we move on. What is the density of water? Density of water is 1,000 kilograms per cubic meter. So if you take a cubic meter of water, that's like about almost like 3 feet by 3 feet by 3 feet, a big old cube of water, that would be 1,000 kilograms. Okay? All right, you ready for the problem? We have a funnel cone-ish looking thing. It's a container, and it's going to hold water for us, okay? And let me give you the dimensions of this thing. It's 10 meters tall, so a pretty tall container. It has a radius here of 4 meters. And inside this container, we have water that's filled up 8 meters high. So we have a water level in here. I'm giving it a little ripple effect for realness, right? Doesn't that look real? Okay, and then I'm telling you the depth of this water is 8 meters. And what I want to do is come in here with a pump and pump all of this water out through the top of this thing. So I want to move all this water out. And the question is, how much work needs to be done in order to empty this container? All right? Does that kind of make sense? How much work needs to be done to remove this? All right, so I've got some cool pictures I put together here. Last night during the very depressing Spurs game, I was throwing together a little bit of code to try and get this thing to show you. Yeah, my parents were there too. It looked good in the beginning. All right, so there's our cone. Make it a little bit bigger here. Yeah, so what's the red thing? Well, everything we've been doing up to this point is like cutting things up, right? Slicing things up. If we wanted to find the area, we sliced it in little rectangles and found a formula for the area of that rectangle, and then we added them all up, right? If we wanted a volume of a solid, we would figure out what one sliver wrapped around would be, found out the volume of that one sliver, and then added those up. Why does this keep moving? Oh, that's why. So what we're going to do here is we're going to say, hey, let's take a sliver of water in here. Now this is an infinitesimally thin slice of water. And in some sort of limit, we're going to let the thickness of that water basically go to 0. So we have this like single layer. But just for like when we sliced the rectangles, we had to show a little bit of width, right? So we've got a little bit of thickness to this. That red piece right there needs to move out, right? I need to move that piece out of this container. And I need to do that for every single layer, right? So you can imagine, start at that layer, find the work to move that layer out. Then that layer, I mean all of these, right? All of them. And so what I'm really saying is imagine taking just that layer and moving just that layer out, okay? Just that layer. So when I move just that layer, its width stays the same and it comes out. But I've got to do that for every single one. Following me or not? Eh? Okay, so let's start orienting some things. The goal here, is to find a formula that would tell me the amount of work it would require for me to move one arbitrary slice out of the container. If I can find a formula for one arbitrary slice, then what I can do is add up all those works together, and that would give me the work for the whole thing. So I would like to start drawing some things here. Let's look at kind of like this cone just as a cross section. If I look at this as a cross section, then I have a water level in here, and then I have some arbitrary slice in here. And again, I'm going to give it some thickness. There's my arbitrary slice. Now I get to start assigning some variables. So I'm going to take this point right here in the middle to kind of be like an origin point. And I'm going to say that the distance from here to the water, right there, to my slice, I'm going to call that distance x. All right? I'm going to call it x. So when I'm talking about this slice, what can x vary between? If I'm going to be taking slices of water out of here, what's the smallest that x could be? 0 would put me up here. This would be 2, wouldn't it? The distance from here to here is 2, because remember, it's 8 high, right? So x is going to vary between 2 all the way down to, what would be the longest x could be? 10, right? 2 to 10 is what x should vary between. But in terms of our formula for work, if work is force times distance, don't we now have what the distance is for that particular slice? If I want to move this slice out of here, this right here is x, right? That's how far it's got to go. So that just leaves us with trying to determine what the force is that's required to move this thing from here to here. All right? And now we start trying to peel apart the stuff we had earlier. What was the relationships that we had with force? Okay. So everyone understand I'm trying to find force right now? Yeah? So force, we said, was ma, but we know that that's really gravity because that's the only thing that we have to fight to get this water out of here. Gravity is a constant, right? So I don't even need to worry about that. So really, I just need the mass of this red slice. If you can tell me what the mass of that is, so what's the mass of that red slice? So this, check, we know what the gravity is. We knew what the d is. So what's the mass? It's the density times the volume, isn't it? It's the density times the volume. So go back, I said, remember when we had the relationships we could solve for mass. I know that this will be density times volume. Now, do you know the density of water? Yes, I gave it to you. It's 1,000 kilograms per cubic meter. So I'm going to write that down. 1,000 kilograms per cubic meter. And look at the way I wrote that. I wrote 1,000 kilograms per cubic meter. I'm writing it that way because I'm going to be canceling some units out here in a minute. And so all we need now is the volume. So what's the volume of this slice? Well, let's take a look. I'm going to draw that little slice for you. I'm going to draw it three-dimensionally. That little slice will look like this. This is a nice little disk, isn't it? Yeah? What's the volume of a disk? Oh, it's like a cylinder, isn't it? Pi r squared h. The volume of this piece is pi r squared times h. Now, one of these things we know. H. H will be the height. And if we're doing these slices, this should be dx. Because remember, x is going to move, isn't it? X is going to move. So this little change right here should be dx. That little infinitesimal width. The only difference is, usually we're used to x going left and right, yes? I decided to let x go up and down. Who cares? I could have called it y, right? Could have called it L, M. It does, well, I wouldn't want to use m because I'm already using m, but you get the idea. It's a dummy variable. So I can say that this is equal to pi r squared times dx. So the only real thing left is to figure out what the radius of this is. So how in the world are we going to figure out the radius of this slice? Is it always the same radius? Is your radius the same all the time? Yes? No? No. Not as x moves, right? As you start moving this thing is going to change. So your radius depends on x. And we actually need to find what that relationship is. Anybody have an idea of how I could connect the radius of that to the x variable? I need some relationship between the two. I'll give you a hint. You can go back to Cal 1. You probably did something like this in Cal 1. You think implicit? Kind of. It's more geometry here. Yeah, triangles. So the r that I'm looking for is actually this distance right here, isn't it? Isn't that r? Similar triangles, good. If I connect this all the way down with the straight line and just look at the right side of this, I have actually two triangles in there. So let me clean this off. I'm going to just erase this. And I'm going to kind of start over with it. And here's what I have. I have one big triangle. I have one big triangle like this. I have my red radius right here. I know the total distance from here all the way down is what? 10. I know this distance from here to here is 4. By the way, that's meters, right? I know that that's r. What else do I know on here that I haven't labeled? What's here to here? That's x, right? That's x. And that means the distance from here to here is what? 10 minus x. Do y'all see all that? Okay, now what I'm going to do is I'm going to draw these two triangles separately. So here's the big triangle, 4, 10. And then over here, the smaller triangle is r 10 minus x. Do y'all see that?